Yeah. All right. Well, it's hard to come after that. But today I wanted to talk about something a little bit different. So this is an area that kind of has caught my interest in the past couple of years, and this is hydrogen. So the enthusiasm for hydrogen really comes from interest of using it as a clean, carbon-free fuel. And when looking out there, if you Google it, you will find that this kind of rekindle with hydrogen came about 2 years ago with this Science article on hidden hydrogen, where, in my opinion, and this is very personal, but Eric Hahn did quite an amazing job at introducing the basics of geologic hydrogen. And then from there, it started to be picked up by the media. So you see it here. France, is hydrogen the miracle solution to the energy transition? Spain, where I'm from, so that was exciting. The Pyrenees may be hiding one of the biggest energy treasures in the world. The UK, limitless white hydrogen under our feet. And very interestingly, even an opinion piece in the New York Times asked, is there a clean mine of gold energy sitting beneath our feet? So I guess my question is, what is all this buzz about, right? Why is it important? And for us, engineers, why should we care? So let's start from basics. Why hydrogen, right? So hydrogen is going to be a key component of the energy transition. Right now, we mainly use it for two things. One is fertilizers, and by far the biggest amount is going to the production of ammonia. And the second one is in petroleum refining, and that's to get rid of sulfur. So current production is a little bit less, as you can see on that plot, than 100 megatons of hydrogen per year. And most of it is coming from natural gas. But if you look out there, there's really talk about hydrogen for nearly every use. Try it, Google hydrogen for the energy transition, and you will find that it's currently being considered for making fuels, for long-distance transport, and that includes boats, trains, airplanes, as a backup battery, also for the generation of electricity and heat, for storage, so really a lot of different applications. And really, as a result of that, the International Energy Agency projects that by 2050, we will be using close to 520 megatons of low-carbon hydrogen. And remember, this is compared to the current 100 that it's mainly coming from fossil fuels and so on. So how do we make hydrogen today? And this is the rainbow for hydrogen. So as I was saying, most of it is what we refer to as gray hydrogen. So we make it by reacting methane with steam at high pressures or from fossil fuels in other ways. The problem is that these processes emit some 900 million tons of CO2 per year. And just for context, this is similar to global aviation. In principle, we could trap this CO2 and sequester it underground, and that's what yields what we know as blue hydrogen. But our highest hopes are really in green hydrogen, which is using renewable solar and wind to split water into hydrogen and oxygen using electrolyzers. Now, the problem with that is that the price of green hydrogen is about $5 per kilogram, which is more than twice the price of gray hydrogen that really tracks the price of natural gas. So pumping hydrogen from underground should, in principle, be much cheaper. And this is partly why proponents refer to this natural stuff as gold. Now, for many, many years, we overlooked this gold hydrogen. And this is partly I don't want to blame the geologists, but this is partly due to them because they thought that it shouldn't accumulate, right? Because hydrogen is the smallest molecule of all. However, free hydrogen has been encountered by humans since ancient times. And you can see here a photo from Turkey where there's been this continuously burning seam of gas that has been known to us for more than 2,500 years. But actually, findings of hydrogen, of natural hydrogen around the world have been done since 1888. And you will see that there's this large concentration in Eastern Europe and Northern Asia, and that's what used to be the old USSR. And this reflects the popularity of an abiogenic theory for the generation of gas and oil. Now, just because we have those green dots there, it doesn't mean that natural hydrogen is not present elsewhere. It's just we were never really looking for it. We were really never measuring it. But I got very excited when 1 month ago, so that was January 25, the USGS released the first ever map showing the potential of geologic hydrogen in the US. And it reveals areas of interest that have the potential to hold the accumulation of hydrogen. And you can see kind of the central region of the United States, from the northwest of Texas all the way to Michigan. Then also you'll have the four corner states of Colorado, New Mexico, Utah, and then the coast of California, and also certain areas in the eastern seaboard of the US. So from these, it really seems like some of the best hydrogen resources in the world are really here beneath our feet. So let's dig into hydrogen. So what are the hydrogen factories and consumers beneath us? So one of the key takeaways from this USGS report is that the Earth is continuously producing hydrogen. And it's doing that through radiolysis, so you can see that number one, during which alpha, beta, and gamma radiation is emitted during the decay of radioactive elements. So again, they split water into hydrogen and oxygen. In the US, the most common radioactive elements are in natural sediments are uranium and thorium, and they're really, really present everywhere. The second one is this process known, so number two, known as serpentization, and that involves the oxidation of iron-rich minerals. And again, it's a process that at high temperatures creates hydrogen. And then there's deeper stuff that I'm not going to get into, we don't know much about, but the real important thing is to notice that once hydrogen is produced and it gets through, it will bump into a lot of different things. Primarily microbial consumption, but it can also get trapped in sieves or be consumed through abiotic reactions by reacting with organic matter or other metals. So the estimates actually suggest that 99% of the hydrogen that is produced will not make it outside, so into the atmosphere, and we have to blame these microbes and these abiotic reactions. So the good news for us is that these reactions should, in principle, we should be able to avoid them. The bad news is that we're not really sure about what are the in situ conditions that promote them in the first place, right? So something that I found interesting, an interesting observation, is that these underground areas that USGS has told us that we should explore because they have the potential to accumulate natural hydrogen, so those are the dark blue areas that you see there, as well as the planned hydrogen production plants across the US, which are shown in yellow, are not infrequently located in regions with high subsurface storage capacity for hydrogen. And these are also areas that have large amounts of evaporites, so salts. These are halite, anhydrite, gypsum that are very, very rich in sulfate. And those are the kind of green, stripy white areas that you see on that map on the bottom right. So really the potential for hydrogen reactions with these sulfate-rich minerals is of interest and also of concern. And the reason for this is that hydrogen is amongst the most energetically favorable electron donor for microbial respiration, which means that it can create opportunities for a lot of biogeochemical reactions. So as you can see in the kind of schematic that I've put there on the right, once hydrogen is either injected underground or it's produced geologically in this gypsum or anhydrite, so sulfate-rich formations, it can really drive a lot of different reactions. And even minimal amounts of sulfate that are present there are going to lead to large amounts of hydrogen sulfide, which is a very toxic and corrosive byproduct. And this hydrogen sulfide can react much more energetically with well materials, and that's, for instance, steel and concrete. It also poses risks in terms of odor, taste, and health if it ever escapes into overlying groundwater, and that's a process known as biosouring. There are also likely locations where CO2 actually accumulates underground, and when it mixes with hydrogen, it can actually lead to a lot of hydrogen consumption to produce methane, which is a very potent greenhouse gas. Now, the impact of hydrogen itself is a little bit less direct, and that's because hydrogen is not a greenhouse gas. But there was this landmark study that was commissioned by the UK government 2 years ago in 2022, where they actually found that hydrogen does react with things underground that do have large impacts. And they were able to quantify that, and they found that the compounded impact of all of that, when you calculate it, leads to hydrogen having a greenhouse global warming potential of 11. So that's compared to the value of 1 that we typically assign to CO2. So, and it's also more than 100% larger than what we previously thought. So I guess what I'm trying to say with this is that if we start doing this underground, we know known but unquantified risks so far, and we also have unknown risks that we should really be considering and discussing about, primarily from an engineering standpoint. So how are we going to avoid leaks of either hydrogen or its byproducts? Are there any seismic effects, for example, that we should be aware of, similar with CO2, right? So kind of to conclude, hydrogen is a truly blank space, and I try to put kind of a white slide. That's how I feel about hydrogen, and it will require multidisciplinary teams to kind of approach it. We will need, as I've kind of highlighted, a good understanding of the biogeochemistry. So that's reaction conditions, their kinetics. Can we catalyze some of the reactions that produce hydrogen while minimizing some of the reactions that consume hydrogen? Geologists are going to play a key role in this as well. Where are the areas that lead to that hydrogen accumulation in the US or around the world? Or where are the hotspots of hydrogen consumption, right? And then, of course, we have engineering. We have to quickly figure out how to access those reservoirs, how to put hydrogen there and then pump it back out. How do we avoid this very diffusive gas from escaping? So the geologists tell us where to look, right? The biogeochemistry tells us what reactions we can speed up or slow down, but it's really up to us, the engineers, to figure out quickly the answer to the one question that I'd like to leave with you today. How do we achieve the US target of 1 million cubic feet of hydrogen per well per day, safely and economically? Thank you.